Hello students, and welcome to the lecture on digital transmission and multiplexing and T-carriers. After the lecture, we will be able to learn the following objectives. Describe digital transmission. Explain pulse modulation. Describe pulse code modulation. Discuss the signal voltage to quantization noise voltage ratio. Describe the delta modulation PCM and differential PCM. Explain multiplexing and T-carriers. Define the time division multiplexing. Describe the T1 digital carrier system. Discuss the European time division multiplexing. Explain statistical time division multiplexing. Define frame synchronizing. Let's start with a brief introduction to digital transmission and multiplexing and T-carriers. Telecommunication deals with the service of providing electrical communication at a distance. The information content of an analog signal is conveyed by the value or magnitude of some characteristics of the signal, such as phase, amplitude, frequency of a voltage, the amplitude or duration of a phase, and so on. This process is used in particular on telephone lines and twisted pair physical connections to increase the data rate. In time division multiplexing, also called TDM, the signals from the different low-speed channels are sampled and transmitted successively on the high-speed channel by allocating each channel in turn all of the bandwidth, even if it does not have any data to transmit. Now let's talk about digital transmission. Digital transmission is the transmittal of digital signals between two or more points in a communication system. The signals can be binary or any other form of discrete level digital pulses. With digital transmission systems, a physical facility such as a pair of wires, a coaxial cable, or an optical fiber cable is required to interconnect the various points within the system. Digital transmission has several advantages over analog transmission. An important advantage is the noise immunity, as digital signals are inherently less susceptible than analog signals to interference caused by noise. Digital signals are better suited than analog signals for processing and combining using a technique called multiplexing. Digital transmission systems are more resistant to analog systems to additive noise because they use signal regeneration rather than signal amplification. Digital signals are simpler to measure and evaluate than analog signals. Pulse modulation. The process of sampling analog information signals and then converting those samples into discrete pulses, and then transporting the pulses from a source to a destination over a physical transmission medium is called pulse modulation. There are 4 different types of pulse modulation techniques. Pulse width modulation, or PWM. The width of a constant amplitude pulse is varied proportional to the amplitude of the analog signal at the time the signal is sampled. It is sometimes called pulse duration modulation, or PDM, or pulse length modulation, PLM. Pulse position modulation, PPM. The position of a constant width pulse within a prescribed time slot is varied according to the amplitude of the sample of the analog signal. It is commonly used in communications over optic fibers, as multipath fading is minimal. Pulse amplitude modulation, PAM. The amplitude of a constant width and constant position is varied according to the amplitude of the sample of the analog signal. It resembles the original analog signal more than the waveforms for PWM or PPM. Pulse code modulation, or PCM. The analog signal is sampled and then converted to a serial n-bit binary code for transmission. Each code has the same number of bits and requires the same length of time for transmission. Pulse code modulation. PCM was invented by Alex H. Reeves in 1937 and is the preferred method of communications within the public switched telephone network because with PCM, it's easy to combine digitized voice and digital data into a single high-speed digital signal and propagate it over either metallic or optical fiber cables. PCM sampling. Sampling circuit in a PCM transmitter periodically samples the continually changing analog input voltage and converts those samples to a series of constant amplitude pulses, which can be more easily converted to binary PCM code. Two basic techniques to perform sampling exist. Natural sampling. In natural sampling, the pulse amplitude takes the shape of the analog waveform for the period of the sampling pulse. The frequency spectrum of the sampled output is different from that of an ideal sample. Flat top sampling. It is accomplished in a sample and hold circuit. Its purpose is to periodically sample the continually changing analog input voltage and convert those samples to a series of constant voltage PAM voltage levels. Sampling rate. Nyquist sampling theorem states that for a sample to be reproduced accurately, minimum sampling rate, Fs, must be twice the higher input frequency, Fa. Signal voltage to quantization noise voltage ratio. The maximum quantization noise is half the resolution. Therefore, the worst possible signal voltage to quantization noise voltage ratio, or SQR, occurs when the input signal is at its minimum amplitude. Mathematically, the worst case voltage SQR is 2. Linear versus nonlinear PCM codes. Linear codes. Magnitude change between any two successive steps in uniform. Resolution accuracy is the same for lower and higher amplitude signal. SQR for low amplitude signal is less than the SQR for higher amplitude signal. Nonlinear. Step size increases with the amplitude of the input signal. More codes at the bottom. Distance between successive codes is greater for higher amplitude signals. Vmax, Vmin is increased. Companding. Companding is the process of compressing and expanding and is a means of increasing the dynamic range of a communication system. Higher amplitude analog signals are compressed prior to transmission and then expanded in the receiver. Analog companding. In the transmitter, the dynamic range of the analog signal is compressed, sampled, and then converted to a linear PCM code. In the receiver, the PCM code is converted to a PAM signal, filtered, and then expanded back to its original dynamic range. Two methods of analog companding exist, also called log PCM codes. Digital companding. Digital companding involves compression in the transmitter after the input sample has been converted to a linear PCM code, and then expansion in the receiver prior to PCM decoding.
Explain what is PCM, which stands for pulse code modulation. In a brief sentence, pulse code modulation is a method used to convert an analog signal into a digital signal so that it can be transmitted through a digital communication network and then converted back into the original analog signal. The PCM process includes 3 steps: sampling, quantization, and coding. In the sampling process, the magnitude of the analog signal is sampled regularly at uniform intervals. The obtained values are called samples. For a 4 kHz voice channel, the sampling rate is 8,000 Hz, which means the signal is sampled 8,000 times per second. The samples will then be converted to digital numbers, as we will see in the quantization process. Quantization is a process of converting the obtained samples into discrete digital values. The most basic type of quantization is called uniform quantization. In a uniform quantization, the vertical axis, which represents the amplitude, is divided into equal-sized steps, as shown in this figure. The range between 1 volt and minus 1 volt is divided into 16 steps. Each step represents 0.125 volt. All the samples whose amplitude falls within a step take the same step value. However, the quantization process introduces an error. This is because that the real amplitude of a sample is replaced by an approximate value. This error is called quantization noise or quantization distortion. In uniform quantization, the quantization distortion presents a problem. For example, let's assume a quantization error of 0.05 volt. If this happens at a high-level signal, such as 5 volt, the noise ratio is 0.05 volt divided by 5 volt, which is 1%. Not too bad. But if the same quantization error happens at a low-level signal, such as 0.5 volt, the noise ratio is 0.05 volt divided by 0.5 volt, which is 10%. Simply put, for uniform quantization, the signal-to-noise ratio is good at high-level signals but bad at low-level signals. That is why non-uniform quantization was introduced. In non-uniform quantization process, the steps are not of equal size. Small steps are used for small signal values and large steps for large values. The purpose of doing so is to achieve that the signal-to-noise ratio is nearly independent of the signal level. This is done by favoring low-level voice over high-level voice. In other words, more code groups are assigned to speech at low levels than at the higher levels, progressively more as the level reduces. This is shown in this figure.
Here we will discuss delta modulation PCM and differential PCM. Delta modulation PCM uses a single bit PCM code to achieve digital transmission of analog signals. Here, only a single bit is transmitted, which simply indicates whether the present sample is larger or smaller in magnitude than the previous sample. If the current sample is larger in magnitude than a previous sample, logic 1 is transmitted, and if it's smaller, logic 0 is transmitted. Differential pulse code modulation, or DPCM, is a procedure of converting an analog into a digital signal in which an analog signal is sampled, and then the difference between the actual sample value and its predicted value is based on previous sample or samples, is quantized and then encoded, forming a digital value. DPCM compression of images and video signals. The DPCM conducted on signals with correlation between successive samples leads to good compression ratios. Images and video signals are examples of signal which have above-mentioned correlation. In images, this means that there is a correlation between the neighboring pixels, and in video signals, correlation is between the same pixels in consecutive frames and inside frame. DPCM's advantages over PCM. A typical example of a signal good for DPCM is a line in a continuous tone image, which mostly contains smooth tone transitions. Another example would be an audio signal with a low biased frequency spectrum. DPCM practical uses. In practice, DPCM is usually used with lossy compression techniques, like coarser quantization of differences can be used, which leads to shorter code words. This is used in JPEG and in adaptive DPCM, or ADPCM, a common audio compression method. ADPCM can be watched as a superset of DPCM. Let's now talk about multiplexing and T-carriers. Multiplexing in T-carriers is the transmission of information from more than one source to more than one destination over the same transmission medium. Multiplexing is accomplished in various domains such as space, time, phase, frequency, and wavelength. Time division multiplexing. With a TDM system, transmission from multiple sources occurs on the same transmission medium, but not at the same time. Transmission from various sources is interleaved in time domain. The two basic forms of TDM are synchronous TDM, or STDM, and asynchronous or statistical TDM, STA-TDM. In synchronous TDM, time slot X is assigned to user M alone and cannot be used by any other user or device. T1 and ISDN telephone lines are common examples of synchronous time division multiplexing. Asynchronous TDM networks assign time slots only when they are to be used and deleted when they are idle. STA-TDM is used in high density and high traffic applications. T1 digital carrier system. A digital carrier system is a communication system that uses digital pulse rather than analog signals to encode information. The following figure shows a block diagram for the Bell System T1 digital carrier system, which is the North American telephone standard. A T1 carrier system time division multiplexes PCM encoded samples from 24 voice band channels for transmission over a single metallic wire pair or a fiber optic cable. The multiplexer has 24 independent inputs and one time division multiplexed output. The 24 PCM output signals are sequentially selected and connected through the multiplexer to the transmission line. T-carrier systems. T-carrier systems provide digitized communication for voice or data traffic across a telephone provider's network. The T-carrier specification defines the layer 1 aspects of the multiplexed communication. The two most prevalent T-carrier systems are T1 and T3 circuits. The digital signal, or DS, refers to the signaling rate and framing of the T-carrier. The basic unit is the DS0, referred to as a channel or time slot. The DS0 channel was designed to support one voice call with a throughput of 64 kbps. Now we will discuss European time division multiplexing. In Europe, a different version of T-carrier lines is used called E-lines. With the basic E1 system, a 125 microsecond frame is divided into 32 equal time slots. Time slot 0 is used for a frame alignment pattern and for an alarm channel. Time slot 17 is for a common signaling channel, or CSC. Statistical time division multiplexing. Statistical time division multiplexing is one method for transmitting several types of data simultaneously across a single transmission cable or line. STA-TDM is often used for managing data being transmitted via a local area network, or LAN, or a wide area network, or WAN. A statistical TDM multiplexer exploits the natural breaks in transmissions by dynamically allocating time slots on a demand basis. Slot size. Since a slot carries both data and an address in statistical TDM, the ratio of the data size to address size must be reasonable to make transmission efficient. No synchronization bit. There is another difference between synchronous and statistical TDM, but this time it's at the frame level. The frames in statistical TDM need not be synchronized, so we do not need synchronization bits. Bandwidth. In statistical TDM, the capacity of the link is normally less than the sum of the capacities of each channel. The designers of statistical TDM define the capacity of the link based on the statistics of the load for each channel. Frame synchronizing. The implementation of TDM is not as simple as that of FDM. Synchronization between the multiplexer and demultiplexer is a major issue. If the multiplexer and the demultiplexer are not synchronized, a bit belonging to one channel may be received by the wrong channel. For this reason, one or more synchronization bits are usually added to the beginning of each frame. Robbed digit framing. Added digit framing is inefficient when a short frame is used in the case of single-channel PCM systems. As an alternative, the least significant bit of every nth frame is replaced with a framing bit. This process is called robbed digit framing. Added channel framing. It is essentially the same as added digit framing, except that digits are added in groups or words instead of as individual bits. Statistical framing. Here, no robbing or adding digits is done. As a signal that has a centrally peaked amplitude distribution generates a high probability of logic 1 in the second digit, the second digit of a given channel can be used for the framing bit. Unique line code framing. Some property of the framing bit is different from the data bits. The framing bit is either made higher or lower in amplitude, or with different time duration. The advantage is that synchronization is immediate and automatic. Frequency division multiplexing. Assignment of non-overlapping frequency ranges to each user or signal on a medium such that all signals are transmitted at the same time, each using different frequencies. FDM is used for combining many relative narrowband sources into a single wideband channel, such as in public telephone systems. Advantages of FDM. In an FDM system, users can be added to the system by simply adding another pair of transmitter modulators and receiver demodulators. FDM system supports full duplex information flow, which is required by most of the applications. Noise problem for analog communication has less effect. Disadvantages of FDM. The initial cost is high, which includes the cable between the two ends and associated connectors for the cable. One user's problem can sometimes affect others. Each user requires a precise carrier frequency. Wavelength division multiplexing. WDM involves transmission of multiple digital signals using several wavelengths without their interfering with one another. This technology enables many optical signals to be transmitted simultaneously by a single fiber cable. It is also referred to as wave division multiplexing. Advantages of WDM. Enhanced capacity as full duplex transmission is also possible with a single fiber. WDM is inherently easier to reconfigure, that is, adding or removing channels. Usage of optical components makes it simpler, more reliable, and often less costly. Disadvantages of WDM. Signals cannot be placed so close in the wavelength spectrum that they interfere with each other. The overall signal strength should be approximately the same for each wavelength, which may not be possible. Light waves carrying WDM are limited to a two-point circuit or a combination of many two-point circuits that can go only where the cable goes. Data compression. Data compression is often referred to as coding, where coding is a very general term encompassing any special representation of data which satisfies a given need. Information theory is defined to be the study of efficient coding and its consequences in the form of speed of transmission and probability of error. Data compression may be viewed as a branch of information theory in which the primary objective is to minimize the amount of data to be transmitted. Data compression has important application in the areas of data transmission and data storage. Many data processing applications require storage of large volumes of data, and the number of such applications is constantly increasing as the use of computers extends to new disciplines. Now in the end, let us summarize what we have learned in this lecture. Telecommunication deals with the service of providing electrical communication at a distance. The information content of an analog signal is conveyed by the value or magnitude of some characteristics of the signal, such as phase, amplitude, frequency of a voltage, the amplitude or duration of a phase, and so on. Digital transmission is the transmittal of digital signals between two or more points in a communication system. The signals can be binary or any other form of discrete level digital pulses. The process of sampling analog information signals and then converting those samples into discrete pulses and then transporting the pulses from a source to a destination over a physical transmission medium is called pulse modulation. PCM is a binary system where a pulse or lack of pulse within a prescribed time slot represents either logic 1 or logic 0 conditions. Companding is the process of compressing and expanding and is a means of increasing the dynamic range of a communication system. Higher amplitude analog signals are compressed prior to transmission and then expanded in the receiver. Delta modulation PCM uses a single bit PCM code to achieve digital transmission of analog signals. Here, only a single bit is transmitted, which simply indicates whether the present sample is larger or smaller in magnitude than the previous sample. Delta modulation, or DM, is a subclass of differential pulse code modulation. It can be viewed as a simplified variant of DPCM, in which one bit quantized is used with the fixed first order predictor and was developed for voice telephony applications. Multiplexing is the transmission of information from more than one source to more than one destination over the same transmission medium. Multiplexing is accomplished in various domains such as space, time, phase, frequency, and wavelength. A digital carrier system is a communication system that uses digital pulse rather than analog signals to encode information.